In Thermochemistry 2, we're going to look at thermochemical equations and stoichiometry. So a thermochemical equation, which I touched on in the last video, it includes the energy change as a part of the equation. So we looked at two examples, one of an endo and one of an exothermic reaction in video number 1. So energy or enthalpy are extensive properties. Now, these were terms that were defined several units ago. Extensive properties, they do depend on the amount of a substance. And if you think about it, how do we express an enthalpy change? Well, it's in kilojoules per mole, the amount of a substance. So intensive properties would be like density of water. Density of water is not going to change as the amount of water changes. Boiling point of water. Well, at sea level, water will boil at 100 degrees Celsius regardless of the amount of water that is being boiled. Those are intensive properties, just to once again distinguish between the two. Let's look here at the electrolysis of water. Now, we did a demonstration outside earlier in this course where we had a balloon that was full of the exact stoichiometric ratios of both oxygen gas and hydrogen gas, and then we ignited the balloon and it released a tremendous amount of energy. So the method that was used to collect the hydrogen gas and oxygen gas was electrolysis, and it required an input of energy. So if we are representing this equation, including the energy in a thermochemical equation, then we're going to write the amount of energy required here as a reactant. So that it requires energy to split water. So energy must be absorbed to break apart these water molecules. And so as you can see in this animation, in this video here, we see the two columns inverted and we see these gases being collected. And I bet you could tell which one is the hydrogen gas and which one is the oxygen gas based purely on the molar ratios of this equation. So as you may have guessed, we're going to be moving into what we've learned thus far about thermochemical equations and thermochemistry and applying what you already know about stoichiometry and molar ratios. So the column on the right would be the hydrogen gas because 2 moles of that substance, of that gas, are being given off, whereas only 1 mole of oxygen gas per 2 moles of water. Okay, so let's look at the reverse of this reaction in which the hydrogen gas and the oxygen gas come together to form water. Well, this gives off a tremendous amount of energy. So by reversing the reaction, we can see in one instance here, we have the fusion where that's giving off energy, and that energy is given off to the system and can be utilized to do work, basically. And this second equation is used in fuel cells. It's used in the International Space Station because it releases energy, whereas the top equation here requires an input of energy. So in class, we needed either a battery can be used for this or some sort of power source can be used to split the water here. So let's look at a practice problem here. Just a reminder, a positive enthalpy is an endothermic, negative enthalpy would be an exothermic reaction. In example number 1, during the electrolysis of water, 0.75 liters of hydrogen gas are produced at standard temperature and pressure. How much energy was required to produce that amount of hydrogen gas? So we're going to be using stoichiometry. So let's start with what we know. Well, we know we have 0.75 liters of gas being produced. We know this is at STP, which means 1 atmosphere of pressure and 0 degrees Celsius. And we know under these conditions, 22.14 liters of hydrogen gas, or any gas for that matter, is in 1 mole of hydrogen gas, or again, any gas under these conditions. So we're able to use dimensional analysis here to factor out the volume of the gas. And now we can look at in 1 mole, all right, we go into our mole ratio, except this is different than what you've done because now we're using energy. So remember, the energy is written as an integral part of the overall equation. So you can think of it as a reactant. So for every 2 moles of hydrogen gas that are produced, it requires 572 kilojoules. All right. So again, this is just a part of the equation. And this overall balanced equation, where 2 moles of water are split to yield 2 moles of hydrogen gas and 1 mole of oxygen gas, overall, for that process, requires 572 kilojoules of energy. All right. So now we have our moles of hydrogen factored out, and we're ending with energy, and we're asked for energy. That means we can multiply everything on top and divide that quantity by everything on the bottom to get an answer of 9.6 kilojoules of energy. Always stop and ask, does this number make sense? Well, sure it does. If 1 mole of the gas is going to be 22.4 liters at STP, and this reaction in problem 1 is only producing 0.75 liters, this is going to be a very small amount of energy that was required in electrolysis to split water into oxygen gas and hydrogen gas. Let's look at example problem number 2. Iron 3 hydroxide is formed from oxygen gas and iron powder, so solid iron. The overall reaction is exothermic, and it releases 826 kilojoules of energy. So we're going to have a negative delta H value. Go back to those graphs in Thermochemistry 1 and think about them. All right, so our products are going to be at a lower energy state. What happened to the rest of the energy? It's released to the surroundings from the chemical system. If a hand warmer releases 200 kilojoules of energy, how many grams of iron 3 oxide were formed? So this is cool because this is the reaction that occurs in like a hot hands, a hand warmer that you can buy at the store, where you open it and you shake it, you expose it to oxygen gas, and then it warms up. All right, that's the result of an exothermic reaction. So in this particular problem, we're told that a hand warmer is releasing 200 kilojoules of energy. Now, in the overall balanced chemical equation, we're told that we will yield 826 kilojoules of energy. So what do we do with all stoichiometry? It must start with a balanced chemical equation. So once we get this balance, we see that for every 4 moles of solid iron, which is iron powder, that combined with 3 moles of diatomic oxygen, we will produce or yield 2 moles of solid iron 3 oxide and 826 kilojoules of energy per mole. Again, that number is for the overall balanced chemical reaction that this will give off, 826 kilojoules. Now, in the problem, we see only 200 kilojoules are evolved. That means that we must have a smaller amount. And so because this problem is asking for grams, you can get out your mole map if you need it at this point in the course and start to look at where we're at. What we're given is energy. We're given energy, and we're asked about how many grams must have been formed. All right, so we're going to be using the molar mass in this computation. Let's start with what we know. 200 kilojoules of energy are evolved or given off to the surroundings. So we need to factor that out. So using dimensional analysis, we can say, hey, for every 826 kilojoules, it requires 2 moles of iron 3 oxide. All right, so that is that molar ratio on the mole map, moles of A, moles of B, except in thermochemistry, we're using the actual amount of energy. So we have our kilojoules that are being put into the equation and put into the dimensional analysis. Now we're going to go and we're going to say we have moles of iron 3 oxide. Well, what's going to be the connection? We know we need to factor out moles. That's right, molar mass. So in 1 mole of this compound, there are 159.70 grams in 1 mole. So at this point, as I've asked you to do throughout the course, you start making predictions about what might be a reasonable answer. We're asked how many grams were formed, and we know for the overall chemical process that we are yielding 826 kilojoules a mole per mole. We have 2 moles here, and the molar mass of 1 mole of this substance is nearly 160 grams. So we're going to have a relatively small number as a result, and we get 77.3 grams of iron 3 oxide were formed when 200 kilojoules of energy were given off from the chemical system to the surroundings. So that would be warming your hands up, okay? All right. Let's go ahead and do our final example problem for this video. The dissolving of ammonium nitrate in water produces a solution of separated ammonium and nitrate ions. This dissolution process yields 25.7 kilojoules per mole of energy. If 240 grams of the compound are dissolved, how much energy is absorbed? Energy absorbed. So going back to our graphs, our products now are at a higher potential energy state, which means it required more energy. So they're absorbing energy. Where does that energy, thermal energy, come from? The system takes in energy from the surroundings, so the surroundings will cool in this endothermic reaction, in which enthalpy will be indicated as a reactant, and enthalpy signage will be indicated as a positive enthalpy change. Now, in this course, we've talked about the dissolution, the dissociation of ions. And now you're being told, or you're understanding, hey, this process in which water molecules are breaking apart, the lattice crystalline structure of the ammonium nitrate, those coulombic attractive forces are being overcome. And then we have new bonds forming between the water molecules and the cation and the anion. We have intermolecular forces now that are occurring, and as a result of this overall dissolution process, energy is being absorbed. This is so cool. Let's look at our dissociation equation. So ammonium nitrate dissociates into 1 mole of ammonium cation and 1 mole of the nitrate polyanion. All right, so we have a 1-to-1 molar ratio here. And now we can indicate the change in enthalpy, and this thermochemical equation is written as a reactant, 25.7 kilojoules per mole for this overall process, which involves a 1-to-1 molar ratio. And now we can start our dimensional analysis in stoichiometry starting with what we're given here, okay? Well, we're given 240 grams of the compound are dissolved into water. All right, so we can start there. What would be the next intuitive step as we're factoring out? You can get out your mole map. You can reason through, we need to cancel grams. Where are we trying to get to ultimately? We're trying to find energy in kilojoules, so that's where we need to go. So in order to factor out grams, we're going to use the molar mass. And the molar mass of ammonium nitrate is 80.05 grams in 1 mole. Now we're on moles, and we can use our molar ratios, except, as I've said now for the 3rd time during this video, this is a little different because you're actually using energy. So for every 1 mole of ammonium nitrate, there are 25.7 kilojoules being absorbed in this dissociation process. This will yield 77.0 kilojoules of energy that is being absorbed. So what is the result in the surroundings? If from a system perspective, the surroundings are going to cool because thermal energy from the surroundings are going into the system, in this case, the dissolution system. So to bring up this schematic again, we see the surroundings are cooler. It's an endothermic reaction. This can actually be expressed as the change of enthalpy dissolution. Change in enthalpy of a solution is another way, because recall in the first video I said there are numerous enthalpy changes that will be discussed not only in this course, but as you continue into AP Chemistry. So for this video, our Georgia Standards of Excellence, we've continued to look at heat absorbed, heat released by chemical systems, but we've also looped back in and we've continued our discussions of stoichiometry. I'll see you guys in class.